In this lecture, we're going to focus on a new class of functions. So far, we have looked at polynomials, rational functions, which are just ratios of polynomials, and trig functions. The trig functions were introduced because they're indispensable for the study of any system with oscillations, from oscillating structures, like buildings and bridges, to electronic circuits, to biological cycles. Our new class of functions is the class of exponential functions. These functions arise when we study populations that grow or decay at a rate proportional to the population at that instant. For example, in radioactive decay, the amount of decay measured by radiation emitted is proportional to the amount of material at hand. For bacteria growing in a petri dish, or in your body, the number of new bacteria over a given time interval is proportional to the number of bacteria present at the start of that interval. In both of these situations, you end up having to use exponential functions to model the growth or decay. We will study some of these models later on, but for now, we study exponential functions from the point of view of pure mathematics. An exponential function needs a base, a positive number a, fixed. And given the base, the function is defined by f of x equals a to the x. What is the domain of this function? Well, it certainly makes sense for x any natural number n. A to the nth is just the product of a with itself n times. We then define a to the 0 to be 1. And a to the power minus n is the same as the multiplicative inverse of a to the n, or if you like, the reciprocal of a to the nth, 1 over a to the nth. So the domain of a to the x is now at least the integers. Now we define a to the power 1 over n for positive n. Keep in mind that a itself is positive as well. A to the 1 over n equals y, where y is the nth root of a. But we have to be careful. For example, if a is 9, then for 9 to the 1/2, which of 3 or minus 3 do you use? By convention, you always use the positive nth root of the positive number a. We also need to prove that the positive nth root of any real number exists and is unique. This is a direct consequence of the completeness of the real number field, the fact that there are no holes in the number line, and we won't go into the abstract details. Okay, so we've defined a to the 1 over n, for n a natural number, and then you can define a to the minus the power 1 over n as this reciprocal, 1 over a to the 1 over n. Then you can immediately define a to the x for any rational x equals p over q. A to the p over q is a to the 1 over q raised to the pth power. So now for a positive, the domain of a to the x is all the rationals, q. Can we possibly define a to the x for all real numbers? The answer is yes, but the proof is quite abstract and again depends on the completeness of the field of real numbers. Here's the key idea, which is quite simple. For a given irrational real number x, assume that we know the decimal expansion of x. For definiteness, say the decimal expansion is x equals 0.3987 and the rest of it as you see there. And of course this expansion goes on forever and never falls into a permanent repeating pattern because x is irrational. Now we just approximate x by the following sequence of rational numbers based on that decimal expansion. R1 is 0.3, R2 is 0.39, R3 is 0.398, R4 is 0.3987. Well, you get the idea. We just add a digit each time and then terminate in zeros, which gives us a rational number. Now form the sequence of exponentials, a to the r1, a to the r2, a to the r3, and so on, as the numbers R1, R2, R3, and R4 are definitely getting closer and closer to that irrational number x, it might follow that their exponentials, a to the R1 and so on, should get closer and closer to a number we could define to be a to the x. That is indeed the case, and the proof is very hard, so we won't go into it here. So now, accepting my claim that the above idea works, we have defined a to the x for all real numbers, given any fixed positive base a. Also, the obvious properties of the exponential, as defined on the natural numbers, carry over to the exponential as defined on the real numbers. For example, for natural numbers p and q, we can just count the number of a's in a product to show that a to the p times a to the q is a to the power p plus q. And furthermore, a to the p raised to the power q is just a to the power p times q. This leads to the rules for the exponential on the real number. For any real numbers x and y with positive base a, the function a to the x satisfies a to the x times a to the y is the same as a to the x plus y, and a to the x raised to the yth power is a to the x times y. A simple appeal to the definitions shows that the following hold for natural numbers p and q and positive bases a and b. A to the power p times b to the power p is the product ab raised to the power p. A to the p minus q, that power, is a to the p divided by a to the q. A to the rational power p over q is the same as a to the p raised to the power 1 over q. And that's the same as a to the 1 over q raised to the power p. These laws, which are quite easy to prove for the natural numbers, again extend to all real numbers. In other words, the same formulas hold with any real numbers x and y replacing p and q. So now we have our new function, in fact functions, f of x equals a to the x for any given base a. In biology, the base a equal 2 is very common, for example. We want to graph these new functions. The graph of a to the x for a greater than 1 looks like this. The graph of a to the x for a equals 1 is just constant, since 1 to the x is always 1. Now, if you want to graph b to the x for b between 0 and 1, you can think of b as the reciprocal of a number a bigger than 1. For example, if b is 1/3, then b is the reciprocal of 3. So the graph of b to the x is just the graph of 1 over a to the x. This means we can look at the graph of a to the x for a bigger than 1, and by taking the reciprocals of the y-coordinate, get the following graph for b to the x with b less than 1. Notice that all of the graphs of exponential functions pass through the point 0, 1, since a to the 0 is 1 for any non-zero a. It turns out there is a unique value of a for which the slope of the tangent line to the graph at the point 0, 1 is exactly 1. And this turns out to be the most natural base to use for the exponential function. This base is denoted by the symbol e in honor of Leonhard Euler, who first introduced it. And the special function f of x equals e to the power x is called the exponential function. E is approximately 2.71828, and I'll let you read the rest of it. Notice also that for a bigger than 1, the function a to the x seems to go towards 0 as x moves to the left. That is, the x-axis is a horizontal asymptote on the left. Also, the function seems to get larger and larger without bound as x moves to the right. We will prove these properties later and show that the exponential function e to the x grows large at a truly remarkable rate as x gets large.